The satellites which send weather updates. Rockets that launch satellites to space. Silent, fuel-efficient, and safer aircrafts. The development, improvement, and operation of these fields will promote our quality of life. JAXA has been conducting the development of cutting-edge aerospace technology focusing on these fields. The history of the supercomputer system begins with barrage-made Datatron. It was installed in 1960. The electronic circuit was vacuum tube. Since 1967, Japanese computer called High-Tech, made by Hitachi, had been used. It used transistor as an element. Then, in 1975, the High-Tech was replaced with Facom 23075, made by Fujitsu, as the succession machine. The element evolved into IC. In 1983, Fujitsu made Facom M380, consisting of the LSI was installed. The supercomputer system, which used the vector-type supercomputer Facom VP400 as the core machine, was born in 1987. The following objective was to develop a supercomputer system with the same capability as wind tunnel experiment equipment. Research and development of the numerical wind tunnel began in 1989 by joint development with Fujitsu. The world's first and fastest vector parallel computer was born in 1993. Later, the supercomputer system called Central Numerical Simulation System, or CENS, was installed in 2002. As time went by, a higher performance supercomputer became necessary. In 2009, JAXA decided to integrate 3 systems, which had been installed at 3 locations, into one system and started to use it as the JAXA Supercomputer System 1. Many significant numerical simulations were performed using this JSS1. The era of the supercomputer system with more than 1 petaflop speed had come. JAXA also began to install a new supercomputer system. Let us introduce JAXA Supercomputer System Generation 2. This JSS2 was named SORA, meaning sky and space, hoping to contribute to research and development of aerospace. Subsequently, in October 2014, we started to phase in a new system. Since April 2016, main system with the capacity of the peak performance 3.49 petaflops has been used as the final phase. The total memory size is 100 TB. SORA MA is also designed for energy saving by the adoption of a water cooling system. The pre-post system, which is used as the visualization machine, is the distinct feature of the JSS2. By using this system, we can visualize a large amount of calculated data quickly. JSS2 has the large memory system, file system, archiver system called JSpace, and so on. Now, let's take a look at simulation results. In order to predict the quantity of the acoustic environment at liftoff, it is necessary to simulate accurately the turbulent flow and the acoustic field around the complex geometry of the launch facility. The injection from the main boosters is represented by the density distribution and the propagation of the acoustic waves by the pressure distribution. Interference between the structure of the launch pad and the sound waves is shown. The Epsilon rocket was successfully launched in 2013. The flow field around the Epsilon rocket, soaring at Mach 1.5, is presented. This shows the surface pressure distribution in 5-degree attack angle. We see higher pressure at the rocket bow. Pressure distribution around the rocket is visualized. The size of the sonic boom can be seen. CFD simulation is utilized to research from the launching of the rocket to flight condition. This is an atmospheric particle simulation. To estimate climate change properly, it is essential to understand the complex role of aerosol on the Earth. JAXA introduced the Global Atmospheric Chemistry Model coupled to the high-resolution, non-hydrostatic icosahedral atmospheric model into JSS2 and is utilizing satellite observation data for data assimilation and model validation. This animation visualizes a flow around an aircraft flying at high angle of attack. The shockwave that appears above the wing during high-speed flight and the separated flow behind the shockwave are visualized. The transonic buffet occurs with increasing the angle of attack. The aircraft do not fly at such a high attack angle in general, though it is vital to know the limit of angle of attack in advance to develop aircraft. The aircraft takes out its landing gears, flaps, and slats when it approaches to the airport. The noise generation physics around the high-lift devices and landing gears is being studied by catching the changes in the airflow. This is the numerical simulation around the landing gear model. The flow is disturbed by the tire axle region of main landing gear and other complex parts. This is a simulation result of the wing with the noise reduction device. First, the case without the noise reduction device. Next is with the noise reduction device. The vortices have changed by the device. By changing the shapes of some parts, we aim to gain the technology of airframe noise reduction. The compound helicopter is a kind of future rotorcraft which is expected to be a very useful helicopter. It is not only capable of vertical takeoff or landing, but also flying faster. Isosurface pressure around rotors is shown. We can understand the complicated vorticity generated from the rotors. Research on numerical simulation will lead to more accurate and reliable analysis.